Hi everyone. So I just wanted to do a brief supplemental lecture going over the normal distribution. This is really probably the most important probability distribution for a variety of reasons. It's important for applications in statistical inference, and interestingly, there's a large number of phenomena, many of them naturally occurring, that can be modeled using the normal distribution. So these are things like height, weight, intelligence, among other things. So the normal distribution does have some empirical value, and in fact considerable empirical value, for modeling known or observed phenomena. That said, there's sort of another feature of the normal distribution that's even more important, and that has to do with what we'll discuss next week with greater precision. The basic idea is that even if you have some measure that's itself not normal, maybe you have a histogram that's highly skewed, or you have something that's bimodal, nevertheless, if we sample from that distribution, if we select sums and averages of these variables in a very precise fashion, we'll be able to construct a distribution that will be normal under certain conditions. So we'll speak about this in greater detail certainly next week. Ultimately, what this does is it forms the basis for statistical inference, and it's for this reason that the normal distribution is incredibly valuable to us. Okay, so more on that next week. Now, the normal distribution can be represented with a probability density function. We do have an equation for the PDF, it's right here. That said, it's probably always easiest just to think of the density function in terms of the graph. So think of the bell-shaped symmetrical distribution with the mean, mode, and median all being equal, and try to visualize the areas that are going to correspond to the probabilities we want to compute. The reason why I say that's important is that, well, in order to determine a particular probability that a normal random variable falls into some interval, we'll be computing the area in the interval underneath the curve. And to compute these areas, it's actually going to be far too unwieldy to do it by hand. So we'd need to use statistical software or a probability table. And for that reason, the actual functional form of the probability density function is going to be of limited value for us, at least for our purposes in this course. One of the reasons why is because it turns out that there's many normal distributions, in fact infinitely many, because we can define anything we want for the mean and standard deviation, which are the only two parameters you need necessary to specify a particular normal distribution. So in principle, there might be infinitely many probability tables that one would need to compute any of the probabilities one might be working with for a particular normal distribution. That's not what we need to do in practice. Instead, what we'll do is we'll just standardize the particular normal distribution we happen to have to work with by subtracting the mean and then dividing by the standard deviation. And what this will do for us is we'll be able to use the standard normal distribution instead, which has very well-known properties, and we have a nice statistical table in the back of any good stats textbook that'll help us with those probabilities. The basic idea is, well, if you begin with a normally distributed random variable x, the transformed random variable z that we will get after subtracting the mean and dividing by standard deviation will be the standard normal random variable with mean 0 and standard deviation 1. Essentially what we'll do to make this happen is we'll subtract off the mean, mu, divide by the standard deviation, sigma, and so to relate the standard variable x to the new transformed variable z, we'll just have this relationship. Z is equal to x minus mu divided by sigma, and that will help us translate or transform any probabilistic statement we might care about x into a statement that's easy to compute instead in terms of the analogous proxy, which is z. Okay, so let's have an example. Suppose we have some normal distribution with mean 2 and standard deviation 8. And further suppose we have a whole bunch of probabilities that we might wish to compute for a variety of reasons. We don't have a probability table for this normal distribution that'll help us directly, and I suppose we could use statistical software, but suppose we don't have a computer. What would we do? Well, what we can do is we can subtract the mean and divide by the standard deviation for any of these x's, which then transforms the random variable in order that we can use the standard normal distribution. So let's consider the first example probability. maybe we want to find probability x is less than 12. So this is going to be some area to the left of 12 on that distribution. And we can think about some of the things we know about how this is going to look, thinking about the graph. Since the mean is 2 and x lies to the right of the mean, we're going to be computing some area that's going to include the entire lower tail, as well as some portion of the area to the right of the mean and to the left of 12. All right, so that helps us visualize what we're going to do. To actually do this, what we can do is we can compute the corresponding analogous z on the standard normal distribution that corresponds to 12 on our original normal distribution. In order to do this, what we'll need to do is we'll subtract by the mean 2 and divide by the standard deviation 8. So we'll compute z corresponding to that value of 12. Okay, so z is going to be equal to 12 minus 2, which is 10, divided by 8, which is 1.25. So this means that the probability that x is less than or equal to 12 is the same as the probability z is less than or equal to 1.25. So these probabilities, and therefore the areas under the curve, are exactly the same. The advantage is the standard normal distribution is far easier to work with. So if we go to a probability table or we go to Minitab, we can now compute this probability and we'll find that it's going to be 0.8944. And indeed, we can do this with all the rest of those probabilities that we might wish to find, or any others. We can always transform the x's into z's and get the areas from the standard normal distribution. So for example, if we want to compute the probability that z is bigger than 1.25, this is a right or upper tail area. If we want to compute the probability that z is less than minus 1.25, this is the left lower tail area. It's going to be the same probability by symmetry. And finally, we can compute a middle probability, the probability that p is between minus 0.38 and 1.25. And in this way, what we've done is we're essentially going to transform any of the probability statements about x into something that's easier to work with about z. So I've gone ahead and I've done these computations for us using Minitab already. And in a second, I'll go through and I'll show you the pictures so you can visualize these areas. Okay, so here's the first one. We have the probability that z is less than or equal to 1.25. This was the analogous one for the probability statement we were interested in previously, which is probability x is less than or equal to 12. So here is our probability, 0.8944, and we see this is our left lower tail area plus some area that's lying between the mean and this other point that we'd find further down the distribution. Here's the next picture corresponding to another probability we were wishing to find. And another, and now the fourth, which is the middle probability. And so what we've done in all these cases is we've transformed some statements about the random variable x instead to be about random variable z, and we were able to use the standard normal distribution to plot these areas really nicely. So I show this to you also at the end of some slides that I added to our recitation handout from this past week, and so you can look through that as well for more information on the link between the z and the x specific to this example. Okay, but at this point what I'd like to do is I'd like us to think more carefully about these z's that are making these computations possible. What I'm going to do is introduce z sub alpha notation, which will be a helpful sort of intermediate step between what we're doing right now and the confidence intervals that we're going to construct next week. So that's the value of doing this. Some value z alpha, corresponds to a point on the measurement axis for which some proportion of the area under the z curve is equal to alpha lies to the right of z sub alpha. So for instance, if we want 10% of the area to lie in the upper tail, we need to find z sub 10. If you want 5% of the area under the curve to lie in the upper tail, you need to find z sub 5. These are just labels for the particular critical values that are going to place alpha percent of the data in the upper tail. And so I've got this table and the corresponding percentiles, alpha tail area, and then the corresponding z sub alphas. And then I'll show you two pictures. I'll show the first one. Suppose we want 10% of the data in the upper tail, and then suppose we want 5% of the data in the upper tail. Why did I choose these? Well, these are going to be, in particular the 5% one, are going to be really useful for the confidence intervals that we're going to be constructing next week. Okay, so z sub 10, this is the 90th percentile. It places 10% of the data in the upper tail. And here's z sub 5. It's equal to 1.6. The corresponding z is 1.645. This is the 95th percentile. It places 5% of the data in the upper tail. And once again, this notation is going to be super useful when we begin building confidence intervals, actually quite shortly. Okay, so two more things to talk about. First, I'll mention briefly how to check and see if data are going to be adequately approximated by the standard normal distribution. The first suggestion is to examine the histogram and see if the intervals within 1 standard deviation, 2 standard deviation, and 3 standard deviations of the sample mean are consistent with the empirical rule. In other words, are the percentages approximately equal to 68%, 95%, and 100% respectively from the empirical rule. Another thing we can do is we can find the interquartile range, the IQR, and the sample standard deviation and take their ratio. So if we calculate IQR divided by standard deviation and get something close to 1.3, then we know we have data that are approximately normal. And the last thing we could do is we could use statistical software to examine a normal probability plot for the data. If the data are approximately normal, then the points will fall approximately on a straight line. So there's a way to do this in Minitab. If you go to, I think it's the calc menu or maybe it's the graph menu, you should check on that, and then you can construct the normal probability plot. The best way to do this is to use statistical software, because computation of the actual expected standard normal z-scores for the purposes here are beyond what we do in the text, and certainly beyond what we do in the class. Okay, so have a look at the slides I've uploaded for the recitation. So what I did is I constructed I constructed an additional example, once again linking the example that I just discussed here, linking the normal distribution with mean 2 and standard deviation 8 to the standard normal distribution with mean 0 and standard deviation 1. I go through a little greater detail in the recitation slides to tie back to what we were doing in recitation. So all right, that's all for now, and let me know if you have any questions. I'll see you next week.